In this video, we use the distance from a point to a set to prove an important result. This is the theorem, which says that if A is not empty, it is opened and also closed in Rn, then the result is A equal to Rn. Okay, so this means that Rn is connected. Okay, so let us have a look on this result. If A is not Rn, if A is not Rn, then Rn can be written as the union of A and its complement. But A is open, and A is also closed. Therefore, the complement of A is also open, because A is closed. So the complement of the closed set A is also open. Therefore, if A is not Rn, then Rn could be written as the union of two empty open sets, which empty intersection. The intersection is empty. So this means Rn is not connected. Therefore, if this result is true, then Rn is connected. Okay, so actually this statement that A equal to Rn, the statement of the theorem and the connectivity of Rn is equivalent. Okay, so in other words, to see that Rn is connected, it suffices to prove this theorem. Okay, of course, it is easy to see that Rn is pathwise connected. We have a remark. As we know, it is easy to see that Rn is pathwise connected. Okay, because Rn is convex. Any segment which endpoint in Rn contained in Rn completely. So Rn is convex, therefore path connected. Okay, and previously, when in our study of the intermediate value property, we see that any pathwise connected space is connected. Therefore, we already know Rn is connected. But now we will prove this theorem to show you an interesting technique. And as a corollary of this theorem, we have the second proof of the connectivity of Rn. Okay, now let's go to the proof of this theorem. So we want to prove that if A is not empty and open and closed, then it is Rn. So we prove by contradiction. If A is not Rn, then there exists some point x belongs to Rn but not in A. Okay, so this is A, and A is not Rn. There is a point x here belongs to Rn but not in A. Okay, then because A is closed, this is our assumption. We have proved before that because A is closed, there must be some point inside the set A, so that the distance from the point to x is equal to the distance from x to A. So by our previous result, there exists some point denoted by small a in the set A, such that the distance from x to A is exactly the distance from X to the set A, which by definition is the infiniment of Y in A, X to Y. Okay, for every Y here, the distance from X to Y is the length of this segment, and Y here. Okay, but there is a point A here. The distance from X to A equal the distance from X to the set A. Okay, this is our previous result. Because A is closed. Okay, now we used another assumption that A is also open. But A is open. Therefore, the point small a is a point in the open set capital A. So small a must be an interior point of capital A. So by definition of interior point, there exists some epsilon positive such that the epsilon neighborhood of this small a contained completely in the set A. Okay, we have a small a here. Its neighborhood contained in the set A completely. Okay. Now intuitively, because this whole neighborhood is contained in the set A. Intuitively, we start from the point A, go a little bit toward the point X. Okay, here is A toward the distance of X a little bit. This point here, this point will remain in the epsilon neighborhood of A. Epsilon neighborhood of A. But the distance from this point to X should be less than the distance from X to this point A. Therefore, this is a contradiction. Okay, because the distance from X to A to the point A is the infiniment of the distance from X to any point in A. Okay, this is the idea. How to express this? How to express this legally? Okay, so let's do this. We take an epsilon, lambda. Take a lambda greater than 1, less than greater than 0, less than 1, such that lambda multiply the distance from X to A less than the neighborhood epsilon. Of course, such a lambda exists. Okay, we can take a lambda satisfies these two properties. Firstly, it belongs to the open interval 0, 1, and also make this inequality valid. Okay. Then, of course, in this inequality, we have used the fact that X not in A and A in A, therefore the distance from X to A is positive. Otherwise, if the distance from X to A is 0, then such lambda, of course, also exists. Okay. Anyway, we don't need this. But I will remind you that actually we have this result. But in our proof, we don't need this. We don't need this. Okay. Let's go back to our proof. We take such a lambda, then we set our point B. Let B be the point I said before. Start from the point A and toward the direction of X to A, which is X minus A. This vector is X minus A. So, and we multiply a small lambda. This B, geometrically, this B is the point from A toward the direction of X. Okay, move a little bit. Okay, that is our B. Then we can check that the distance from B to A is the lambda X minus A, right? But this is the absolute value of lambda multiply the distance from X to A. the norm of x minus a. But lambda is positive, therefore this is lambda x minus a. Okay, this by our choice of lambda is less than epsilon. So this means b is contained in the epsilon neighborhood of a. Therefore b is in a. Because the whole epsilon neighborhood of a is a subset of our capital A. So we have find the point b in the set A. We will prove that the distance from x to b strictly less than the distance from x to a. Therefore, once we prove this, we get a contradiction, which is the choice of a. Because by our choice of a, this distance from x to a, the norm of x minus a, is the infiniment of the distance from x to any point in a. But our b is in the set a. So this is a contradiction. So we try to prove this final inequality. The norm of x minus a less than that of x minus the norm of x minus b less than the norm of x minus a. We'll prove this in the next page. So to prove this inequality, we need to estimate the distance from x to b. But our b, what's our b? Our b is a plus the lambda x minus a. This is our b. Therefore, this is x minus a plus lambda x minus a. And so this is 1 minus lambda x minus a. So by the property of norm, this will be the absolute value of 1 minus lambda multiply the norm of x minus a. So this is 1 minus lambda. We should write the absolute value of 1 minus lambda, but our lambda is positive and less than 1. So 1 minus lambda is positive, therefore we don't need the absolute value. Okay, then this. But x minus a, lambda is between 0 and 1, so this factor is less than 1. So this is strictly less than x minus a. So this is the inequality we want. So this proves our final inequality in this page. So our a is point in capital A, so that the distance from x to this point small a is the infiniment. If a is not Rn, in this argument we can find an a in capital A, so that the distance from x to a is this infiniment. But because a is open, we can find a point B whose distance to x is strictly less than this x minus a, the norm of x minus a. Therefore, this is a contradiction. This contradiction tells us that the assumption that a is not Rn is not true. Therefore, a must be Rn. This complete the proof. Okay.